Week 8, Quadrilaterals.
This week is all about quadrilaterals, which are just four-sided figures. The first thing we want to do is construct one of each of the three types of quadrilaterals. So I'm just going to go to the polygon tool. And the first type of quadrilateral is a convex quadrilateral, which is the most common. I know it's convex because each of the vertices basically occurs on the interior of the opposite angle. So for instance, A is on the interior of BCD, B is on the interior of ADC, and so forth. Another way that you can look at what type of quadrilateral it is to create diagonals. So in a diagonal like this, those two diagonals are going to be inside of the figure. So let's take a look at another polygon, which is the crossed polygon. And instead of going in order, a cyclic order, I'm going to simply just cross to make the third vertex. And again, we can see that this is a crossed quadrilateral. You can also create the segment. And notice if I go to opposite sides, opposite vertices, those diagonals occur not really diagonally, but outside of the figure. The last type of figure is a concave quadrilateral. And basically what it is, it's kind of like, whoops, don't do that. It's kind of like the convex, except that one of the vertices is going to kind of come in. So we can see something like this. If I created those diagonals, I to K and L to J, we can see that one of the diagonals occurs within the figure on the interior and one on the exterior. So these are the three types of quadrilaterals that we'll be looking at. The most common, obviously, is the convex. So for our first theorem that we're going to prove this week, we're actually making we're dealing with a midpoint. Oops, don't do that either. So we're dealing with a midpoint. So what I'm going to do is I'm just going to find the midpoints of those segments. So the midpoint of AB, oops, having a little trouble with my clicking today. The midpoint of AB, the midpoint of BC, of CD, and DA. And then I'm simply going to create a polygon from those. Again, another convex polygon. And the theorem, Varignon's theorem, says that this, in fact, is a parallelogram. And I can see that it appears to be a parallelogram, but we, in our next proof, are going to take a look at that theorem and prove that it is, in fact, a parallelogram. So for our first proof, we are going to prove that that midpoint quadrilateral is in fact a parallelogram. So as you can see, I have the exact same picture we constructed together. We have let quadrilateral ABCD be a quadrilateral with midpoints EFGH on AB, BC, CD, and AD respectively. We're trying to prove EFGH is a parallelogram.
So how are we going to go about doing this? Well, we're going to use good old Euclid's proposition BI2 as we have so many times before. If I take a look at triangle ABD, within triangle ABD, I know that E and H are midpoints, and therefore AEH is a similar triangle to ABD in a 1:2 ratio, and therefore I can say that these two lines are parallel. In the exact same way, if I look at triangle BDC, I can show that FG is parallel to BD. So obviously, I can say that EH is parallel to FG. And I can do the exact same process in the other direction to show that in fact there is a line that connects AC, and I can say that AC is going to be parallel to EF, and that AC is going to be parallel to GH, and therefore opposite sides are parallel, and I in fact have a parallelogram. So that's how we would go about proving that the midpoint quadrilateral of any quadrilateral is a parallelogram.
For this question, we're not going to go through the whole proof together, but we are going to take a look at the strategy that we would use. So for instance, here we have a circle, we have a cyclic quadrilateral, which means that the vertices do actually follow an order A, B, C, D. And to construct this, I just made a circle with 3 points, and then I added another point D. So we can see that D is movable, but if I move A, B, or C, it moves the whole circle, but that's fine because everything's on the circle. And then I'm going to create a polygon A, B, C, D, and back to A. So that is a cyclic quadrilateral, and all of the points are on circle Y. We are trying to prove that the measure of angle ABC, which is this angle down here, so let's go ahead and measure the angle, ABC, and we're going to make that 0 to 180, and the measure of angle CDA, so CDA, that if I add those together, that I get 180. So of course we can actually find that. We can come down here and say alpha plus beta, alpha plus beta, and we see that it's 180, and we could obviously show that as well on the screen, but we're not going to do that here because this is less about the construction and more about the proof. So again, how are we going to prove this? Well, we can make some diagonals, and then I can use the inscribed angle theorem. So for instance, if I make these diagonals, I can then look at ABD and ACD. So ABD and ACD. What do I know about those two angles? Well, that they're both inscribed to the same arc. So let me show you the angle that I'm talking about. ABC obviously opens up to arc AD, and ACD opens to the same arc. So we can see on GeoGebra that in fact those two angles are congruent, but that's exactly what you'll do, is you'll continue to use similar arcs to say these two angles are congruent, these two angles are congruent, etc. And then you'll just start adding them up to equal 180, because obviously we know the angle sum theorem tells us triangles are equal to 180. So you can decide how to go about getting to that 180, but obviously it's fairly easy to show that those smaller angles are congruent based on the inscribed angle theorem.